What we want to cover today is the concept of a geometric sequence. Now, you previously saw an arithmetic sequence, which came into effect when we were dealing with a constant rate of return, which was associated with a linear um, equation. So, since we're dealing with exponential functions, the concept of a geometric sequence you should see coming into effect is when we have an exponential function. So let's take a look at the following examples. We have the following 5 sequences here, and let's see what's happening. In the first one, you should see we're multiplying by 2. In the second one, we're adding 2. In the third one, we're multiplying by a half. The fourth one, we're adding 5. And in the last one, we're multiplying by negative 1/10. Okay? Now, in a sequence, any sequence, what we define it as is a sequence is an ordered list of numbers that forms a pattern. Now, we've dealt with that before. And if you might remember, which is a very important concept, the term of the sequence is each number in the list. Because what becomes important is drawing a relationship between where a number is and its value. A geometric sequence is a sequence in which the ratio of any term to the previous term is a constant. Well, what's ratio mean? Ratio is just a fancy word for division, okay? The common ratio is that constant ratio. So, if we go back to the do now, which of these 5 are geometric sequences? And hopefully you're going to see that it's A, C, and E, because each term is obtained by multiplying the prior term by a constant. Or if I divide 6 by 3, 12 by 6, etc., I get a constant value of 2. So when you look back, A, C, and E. Now, what we want to do, which is what we did for an arithmetic sequence, is to figure out a formula to be able to figure out any term in the sequence without having to find all of the other terms. So let's talk about that. As you might remember, just to refresh, we have notation that we use, that subscript notation. And A2 is A1, 6 is A2, etc. Now, hopefully you're going to see that what we're doing is multiplying by 3, so that the next term, A6 is 486, and A7 is 1458. Okay? Now, what we want to do is, let's come up with our formula here. And if you might remember, in an arithmetic sequence, we had a recursive and an explicit formula. And we're going to do the same thing here. So, if you look at what we did, the value of term 1, which is A1, is 2. And continuing the concept, A2 is A1 times 3. A3 is A2 times 3. Term 4 is A4 is A3 times 3, etc. I'll continue this out one more time. So that what we can write as our recursive formula is that to find a term, we would take the term right before it a n minus 1 and multiply it, in this case, by 3. Okay? So, same concept. A recursive formula is a formula to represent, in this case, a geometric sequence as a function rule that relates each term of the sequence except for the first one, because there's nothing to relate for the first one, to the one before it. And we write that as a sub n is equal to a sub n minus 1 times r, and r is our common ratio now, as opposed to common difference. Okay. Now, let's take this another step. Let's use this strategy to develop what's more important, the explicit formula. Okay? So, going back, we had 2, 6, 18, 54, 162, dot, dot, dot. This is a sub 1, a sub 2, 3, a sub 4, and a sub 5. Okay. Now, if we look at this, we know that a sub 1 is equal to 2. And the other thing that's important, like we did before, is our common ratio is 3. So a sub 2 is 2 times 3. A sub 3 is 2 times 3 times 3. A sub 4 is 2 times 3 times 3 times 3, which is 2 times 3 squared, which is 2 times 3 cubed. And you'll see why that's important. So hopefully you'll see that what's happening here is that what we are doing to figure out a sub n is we're taking the first term again, we're multiplying it by the common ratio, okay, which in this case is 3, and we're multiplying it n, or we're raising it to a power of n minus 1 times, okay? So that gives us our explicit formula for a geometric sequence. And similar to what we did before in arithmetic, is a function rule that relates each term of a sequence to the term number. And in general terms, a sub n equals a sub 1 times the common ratio to the n minus 1 power. Okay? So, let's take a look. What's r in this example? R is 3. I want to find a sub 10. So a sub 10 is the first term, 7, times 3 to the 10 minus 1 power, which is 137, 781, if I did my math correctly. All right. Next two examples, I want to write a recursive and an explicit formula. So, you always want to represent your common ratio as a function of multiplication. So I know you're dividing by 3 here, but what you're really doing is multiplying by 1/3. So my recursive formula is a sub n equals a sub n minus 1 times 1/3. My explicit, which is more useful, a sub n equals my first term of 81 times 1/3 to the n minus 1 power. And if I want to find a sub 10, it's 81 times 1/3 to the 9th power, which is 1 over 243. Okay. And lastly, what's happening here? I'm multiplying by 3. I want to find a sub 10. It's 1 over 36 times 3 to the 10 minus 1 power, which is 546.75. Okay, so what we covered today was the concept of the geometric sequence. It's part of this unit because as you saw, a geometric sequence is represented in exponential form.